Okay, so this is a special topic on table time. Confusing subject material. I've gotten some email questions about it, so this is going to be a talk hopefully to address it, clarify it. I'm going to, of course, focus on what I think is testable. So, one of the prior lectures, this table exists, and it shows the signal-to-noise ratio, spatial resolution, and table time trade-offs. Now, this is probably the single most highest yield table in all the MR physics and the books and the lectures, everything, as far as what is raw and testable. Okay, so specifically this point right here is what causes a lot of confusion, because people say, hey, if I'm making thinner slices, that means there's more slices, that should mean there's more table time, but you're telling me that it's not really affecting table time. So let's just review this real fast. So, this is sort of the concept here, is that, different slices, time is going by as we go through. So just a quick refresher on how the thickness of a slice is determined. Okay, so to give each slice a thickness, a band of nuclei must be excited by an excitation pulse. The slope of the slice-select gradient determines the difference in precession frequency between 2 points on that gradient. So a steep gradient slope results in a large difference in precession frequency between 2 given points on the gradient, while a shallow gradient is going to result in a small difference in frequency between the same 2 points. On a certain gradient slope applied, RF pulse transmitted to excite the slice must contain a range of frequencies that match the difference in precession frequency between those 2 points. That frequency range is called the bandwidth. That's why it's not just one dot. It's a range. It's a bandwidth. And as the RF being transmitted at this point, it's specifically called a transmit bandwidth because that's the one that's transmitted. All right, so let's sort of cartoon this out and take a look. So this is a steep slice-select gradient, and here is a transmit bandwidth. So as the points sort of intersect here to here, as it crosses that line, that is your slice thickness. Now let's see what happens when we change this slice-select gradient from steep to shallow, keeping the transmit bandwidth the same. Okay, now it's all the way out to here, so it's got thicker, right? And then here's a situation where we kept that same shallow slice-select gradient, but instead we narrowed our transmit bandwidth. Okay, and you can see that right there, it got thinner. So taking a look here and just comparing those things out. So a thin slice, to get a thin slice, you're going to want a steep slope or a narrow transmit bandwidth. So either this or that. To get a thick slice, you're going to want a shallow slope, or you could, and I didn't draw this, but you could compare it from here to here, a thicker transmit bandwidth. So again, that would increase the table time, right? So this is a concept that I use. A true MR PhD in physics head might explode by looking at this, but this is the way I want you to think about it. So you've got a slice select, or you've got a frequency encoding plane and a phase encoding plane. So let's say that frequency and phase. Phase is that's the long one. That's the one that really contributes to time, right? So at each one of these blocks here, we've got to go through the same deal, okay? Same deal for each one. Now let's say that we make thinner slices, okay, like that, all right? It's still the same amount of time in that phase encoding total phase. You may have more individual phase encoding steps, but the time in each one is smaller, but it's the same distance overall. Does that make sense? Like if you're running laps on a track, instead of having one giant lap that equals a mile, you've got 4 smaller ones, but your time is still the same, maybe with slight differences given the fact that there's you're making a tighter turn or whatever. See, here's a trick. Everything that I'm talking about right now is this idea of a 2D imaging. So for the purpose of multiple choice, I'll say this a couple of times because it's important. For the purpose of multiple choice, unless specified otherwise, assume that you are doing a 2D type of MR acquisition, okay? So we've got a phase encoding, frequency encoding, and then you've got multiple it's two-dimensional, and then you go on to the next one. So this is 2D, all right? And when you're dealing with that, this is the formula to remember. TR times your phase matrix, I like that terminology better, times your NEX. So just a refresher here, the TR is the measurement, typically in milliseconds, that is the time between each RF pulse. Your phase matrix is the system is collecting data from the slice once for each phase encoding step. And the NEX is the number of times each set of phase encoding steps are repeated. So there's a number of excitations. Now, that is in contrast to this idea of volume imaging, or 3D, okay? So volume imaging is awesome. It's really, really useful for lots of different stuff. If you are doing rectal cancer staging, it's really, really nice because you can do basically NPR stuff like you do on CT, and change the planes and get things straight in axis. I think it's pretty useful with brain MR stuff too. There's lots of, so it's great. It's really good for very small lesions because the slice thickness can be drastically reduced compared to conventional imaging. There's no slice gap. In conventional imaging, the slice thickness affects the signal-to-noise ratio. But in volume imaging, the entire volume of tissue is excited, and the volume contains no gap. So the signal-to-noise is superior, and you've got fewer excitation steps can be used. The other main advantage, like I said, is that it's not acquired in a straight slab. It is acquired acquired in a big slab, like a cubic slab. And because of that, you can manipulate the anatomy within that volume in any plane and in any angle of obliquity. Now, so why not just do it all the time? Because there's a big disadvantage, which is the scan times are relatively long, and your formula is different. So the formula, go back to this thing, you're not just dealing with a phase encoding and a frequency encoding direction, you also have a slice encoding. So it's taking into factor those slices. So does slice thickness affect table time? Yes and no. If it's a 2D acquisition, it does not. If it is a 3D acquisition, then it does. And I want you, for the purpose of multiple choice, to assume always that you are dealing with 2D unless otherwise specified. So when you see those charts, there's a chart in Crack the Core, there's a chart in one of the prior MR lectures, or just Google it. Any chart, literally any chart that you'll find, when we talk about slice thickness, it's going to have the column that has does this affect your table time, and they will always say no. But sometimes it does, and that is when you're dealing with 3D imaging. So just always assume that it's 2D, because remember, the MR physics is basic for this, okay? Basic, think basic, all right? But that would be the trick. All right, so that's gonna wrap this one up.